Okay, so last time we were doing this lists, right? We were playing with lists. And then we kind of learned a little bit about those different loops, right? We did that beer on the wall activity. And A, my A, B, C, D. Right, so there we go. Here's using a for loop. And like last time I was saying, we've got for loops, we got while loops, and we have a couple of other those keywords like range, enumerate. I'll review them here again for a quick sec. The while loop is like your general purpose loop. Okay, you can make it do whatever you want. For loops, you can make a for loop do whatever you want, really, however you hack it to do what you need it to do. But for loops are often used for situations like this, where it's like for each thing. You can think of a for loop as a for each type thing. For each thing in my collection of things. So for each element in my list. It also worked with strings, but of course in that case, the collection of things are individual characters in the string. But that's how it works. But we saw that, like, well, that's great, but you remember how I did that linear search example where I said, okay, tell me if the thing exists. Okay, great. But now tell me where it is. And the problem with this style is I don't know what index each thing is. I can by simply like creating a counter and incrementing it every time. I could do that. But I also showed you that enumerate my list. And then, well, here, we could do it like this. We can use enumerate. But what you'll notice is the thing becomes a little bit different. The thing becomes this right here, this syntax. It's a tuple. It's kind of like a list. It's a tuple. It's a pair of information where you've got the index followed by the thing at that index in your collection of things. So that's pretty neat. Now, usually what we do when you're using enumerate is you unpack the tuple right in line here. So watch what I do, like I and then thing. So I could do I, comma, thing. So now I've unpacked it. Because this was giving me a pair of information, and if I put two things in here, it'll automatically assign the first thing to the first one, and the other thing to the next thing, which is thing in this example. Neat. And sometimes, if you have a loop, and you just need to run a loop like 50 times, a really easy way to do that is like for I in range 50. Print I. And I hit run, and it's going to do that. Okay? This is a really quick and dirty way to just make like a counting for loop. But if you think, oh, so this acts differently than what we're used to, not really, because range kind of gives you like a list of the elements 0 through 50, 0 through 49. And then it's like for each thing in that collection of things, so it just counts, right? But it still is technically doing, like creating this like iterable object. It's a whole thing. Okay, cool. Any last questions about these lists and these loops? We're not done talking about lists, and you're going to be using lists a lot. Now, I hinted at this topic a few times where I'm going to go and give you some intuition as to why lists are a little bit different. And I'll show you what I mean. If I say A equals 5, print A, and then B equals A, print B, and then B plus equals 1, print B. And okay. Look at this code. Clear output. Nope. Clear. Look at this code and lock in your head what you are going to see. Okay? And pardon me while I check to make sure I'm recording. Okay, I'm good. So look at this code. What do you expect to see? I'll give you like 10 seconds. Lock in an answer in your head. You don't have to say it. Okay? Nothing about this code should shock you. There's no twists and turns in this. It's straightforward. There. Raise your hand if you were right. Good. So why? Well, A is 5. Print out A. 5. B equals A. Okay, B is 5. Print B. 5. B equals B plus 1. Okay, so 5 plus 1 is 6. B is 6. So A, well, A is still 5, and then we modified B. Right? Cool. Now, let's do something similar with lists. A equals A. No, let's do like my list. B, C, D, E, F, G, H. Perfect. Okay. Print my list. My other list equals my list. My other list. Okay. Now, look at this code. I'm not going to hit run yet. I'll give you 10 seconds. Look at this code. What do you expect to see? There's no tricks here yet. Okay, I'm going to hit run. Raise your hand if this is what you expected. Okay, cool. Raise your hand if it's not what you expected. Okay, so far so good. Now here's where you might get a little surprised. Mother list at 0 is going to be equal to x. Okay. Okay, actually, it's not going to get weird yet. When I hit run, what would you expect to see now? All I did was add these two lines here, right? Let's clear this output. Okay, I'm going to hit run. So far, so good, right? Now I'm going to go down here and also print my list. Okay? My list will be the one on the bottom this time. Where up here, like I put A before the B, but whatever. I'm putting my list there. Okay? Look at this code. Lock in your answer. What do you expect to see? Raise your hand once you have an idea. I'm not going to ask you. Okay? Raise your hand if you were right. One person, two people were right. Very good. Raise your hand if you were wrong. From the looks on your face, you're like, what? I'm going to show you today why it did this. And after I show it to you, it's going to make perfect sense, and you're going to understand what's going on. And it all comes down to the fact that when I say something like my list equals that list, the thing stored where my list is, like the actual value stored in my list, is not a list. It's a reference to a list. So now I'm just showing you the idea, like the problem. Now I'm going to explain what's going on. Any questions before we jump into this, though? So you probably should pay attention real good for this topic, because this is how things are going to work for the most part in programming. Unless you're dealing with like primitive types, but more on that in a moment. We need to be aware of what is actually stored in our variables. Now, warning, this warning is I'm going to be explaining how these things work as if, like traditionally speaking. The way this actually works in Python is a little bit different, but funnily enough, Python, although it works different, it goes out of its way to act the way it used to work for consistency reasons, like traditionally, okay? But anyways. Also another thing too, this is just to hedge against anyone in here that's going to go like, actually, usually when we're talking about like RAM, Although there's nothing wrong with using decimal numbers, base 10 numbers. There's nothing wrong with that. Often we use hexadecimal numbers, which is a fancy way of saying we use the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F to like count a little bit. It's a little weird, but it's what we do. And it all connects to binary because half a byte, right? This is 0 in binary, right? 1, 2, 3, 4. And if I were to go like 1, 1, 1, 1, this number is 15 in binary, which we represent with an F, right? So you can easily represent 4 bits with 16 unique symbol. It's a whole thing. It doesn't matter for our needs right now. It really doesn't, but just usually we refer to these things with hexadecimal. For right now, I'm just going to use decimal numbers, okay? All right. Oh, let me show you a quick example of that here, right? So if I say, how many of you have accidentally done something like this? What this function does is useless. Return 5. This is a stupid function, okay? All it does is if you call it, it gives you the number 5 back. Great. But how many times have you done this? Yeah? How many of you have done that accidentally? So what did I do? Well, I never actually called the function, right? Why did I not call it? Because I need to put like parentheses there to call it, right? I'm just saying, oh, well, there's a function. And Python goes like, okay, great, that's a function. And here's an example of a number that's in hexadecimal. It's a big one. Interestingly enough, this is like where, it's complicated, but effectively this is like where in the computer this function is stored, which is kind of neat. The OX means like this is a hexadecimal number, and then it's like a 7FF2BA8171A0. Don't ask me what that is. It's a big number. All right, back to this. So here is an idealized view of memory in the computer. When we talk about, like often, if you hear like RAM, raise your hand if you've heard RAM before. Yeah, okay, RAM. RAM, random access memory. Often when I'm talking about memory, usually people are referring to RAM. Though we could be talking about like longer term memory. That would be things like solid state drives or hard disk drives, right? But in general, we're talking about RAM. And inside of the computers, we use usually dynamic RAM. DRAM, it's a whole thing. Doesn't matter. But we like to think of memory kind of as like a giant, you could kind of think of it as like a giant list, okay? Where there are memory addresses, unique addresses. So if I say, go to memory location 127, it would mean like this, okay? It would mean there. Think of it like mailboxes on a street, okay? You can go to each mailbox, starting at 0, going up to like a bajillion, and I can put information in each mailbox. But the mailboxes have a fixed size, okay? I can't, like, look, I've got a delivery coming from Amazon today. There's no way it's going to fit in my mailbox, though, right? It is what it is, right? That's okay. They'll put it at the front porch. It's fine, right? But the point is, there is a fixed size. You can only put so much inside a mailbox, right? This isn't shocking anybody. Same idea here. Just we idealize it as like, well, this goes on forever. It doesn't, but we pretend it does. So we have addresses and then the contents, what's actually stored there. We'll refer to this as RAM. I've got these dots here to mean like it goes on forever. And then here it says contents. That doesn't necessarily mean that there's a C at memory location 126. It's contents, okay? And it goes on forever, but not really. I've used the phrase primitive type before. This is a word or a statement, whatever, to mean things like integers, floats, booleans, okay? Basic data types. Strings are not primitive types. Lists are not primitive types. Those are objects, right? Remember we learned a little bit about objects, right? But primitive types, they're your basic things, okay? And I kind of showed you, remember how I showed you that with 8 bits, like how the number 97 in lowercase a mean the same thing, right? It's kind of like, that's how, like primitive types are all actually like the same. It's just how you decode it, matters. They're different. But in terms of the zeros and ones, it matters on like, well, is that an integer or a character, right? It depends on how you decode it. All right. So let's say we have a single integer x. Doesn't matter what it is. An integer is a primitive type. In many programming languages, integers take up 32 bits of memory. 32 zeros and ones, right? I drew 4 here, so imagine there's like 8 times as many. Yeah, right? So that would be 32 zeros and ones. So like, for example, that number right there. Okay, it happens to be 709,582,100, but we could represent that in binary with 32 zeros and ones. Okay? Now, since we know how much room our basic integers take up, 32 bits, I can divvy up my RAM into nice, consistent chunks. All right? Now, usually our computers are byte addressable, it's a whole thing, but let's pretend each one of these can hold 32 bits of information, let's say, okay? So yeah, we can easily put integers in the mailboxes that can fit 32 bits in it. Perfect. If I had a number that required 33 bits, it ain't gonna fit. But 32 bits can go nicely in those mailboxes. Again, if I broke up each chunk of RAM, each address into 32 bits, if I were to go and say x equals 17, this is what the computer's going to do. It's going to take the value 17. Your operating system is going to go and find a place in RAM where it's like, oh, okay, let's put it here. We don't really have control over where it puts it. The computer will find a spot for it on its own. It's fine. That's good. That's nice. We don't want to have to deal with that. That's complicated. But it's going to find an open place of RAM, and it's going to create a label for that place. The fact that I called this X, it doesn't matter. The fact that this is at address 126, it's entirely arbitrary. It doesn't matter. The fact that I made it 17, it doesn't matter. This is just an example. Don't think that any of this is meaningful in any way other than this is our state of our world right now. If I wanted to copy the value of x into another variable, I would write something like y equals x. And then this what happens. Listen carefully. If I say y equals x, the computer will go and copy the contents where x is, 126, and put it somewhere else, where y is, okay? So it copies the contents at the memory location with the label x, and it places the copies somewhere else, okay? So it goes and it says, there's a 17 here, and I'm going to copy it and put it there. Why 129? It doesn't matter. This could be way further away. It doesn't really matter. The point is it's just somewhere else. It makes a copy, and we've got another label associated with it, okay? So the point is it copies the contents at that memory address and puts it somewhere else. Okay, right? Nothing crazy. Makes sense. And that's what I showed you like up here. Okay? So far, so good. Any questions up until now? We are in the safe place right now. We're about to venture into where things are weird, except they're not. They work exactly the same way, kinda. Any questions? All right, so we've got a bit of a problem. I want lists, right? And let's say I have a list of 1, 2, 3, 4, 5, 6, 7, 8. 8 integers, okay? I know they're labeled A through H. They're just labels, okay? But let's pretend they're integers. And we know that integers take up 32 bits. We also know that each memory location can only fit 32 bits in there. But I have 8 times 32. So how can I put a list into one mailbox? The answer is you can't. You can't do it. It's the same thing with strings, right? Characters take up so much room. Now, if you have a string with 10 characters in it or 1,000 characters in it, it's going to take up a different amount of room. The point is, you can't put it into one mailbox, okay? It's the way it is. Is that clear? Is there any ambiguity about that? It would be like telling like 30 people to sit in this one chair. It ain't going to happen. So what do? Well, okay. Since memory is divided up into 32 bits, we need 256 bits of information to store 8 sets of 32 bits, right? 8 times 32, I guess. So here's what we're going to do. Here is the solution. This solution, to be clear, is not a solution in the way that, like, mathematically, this is how it works. No, this was a design decision. This was an engineering decision on how to solve this problem, okay? It's not like a fundamental truth of the universe, like how if you do a linear search, like, what I mean by that is, I showed you the linear search algorithm. If you follow that algorithm, you will absolutely find if that thing exists or does not exist in your list, right? And if I say, why? You're almost like, obviously, because it's the way it is. It's like fundamentally true, right? The solution here is not like a fundamentally true thing. It's just this is an engineering decision someone made, and it's a good one. So what we're going to do is instead, we go and find a chunk of RAM where I can put, traditionally speaking, a contiguous chunk of RAM. It doesn't need to be the case anymore, but for our demonstration purposes, it'll go and find a chunk of RAM where I can fit all of that data in. All right? To be clear, you've got like bajillions of memory locations. How much RAM, who in here knows how much RAM they have in their computer? How much you got?
My laptop, 16 gigabytes.
16 gigabytes. So how many bytes is that? Billion, right? Billion. So 16 billion. And your computer's byte addressable, so you've got 16 billion and change mailboxes. It's a lot of mailboxes, okay? Cool. The point is, we go and we find a chunk of RAM. We go, okay, put the A, the B, the C, the D, E, F, G, H. Great. There's 8. 1, 2, 3, 4, 5, 6, 7, 8. Great. Okay? That's how we do it. But, so what do we store? Like if I say something like Z equals that list, how is it going to work? So, okay, we put each integer into here. Again, these are letters, but pretend they're integers. It's just a label. Keep track of the fact that the list starts at memory address 677. That's what we're going to do. We're going to keep track of where does the list start and where does it end. So if I were to do something like this, the computer is going to go find a contiguous chunk of RAM. All right? And it's going to create a variable, like I said, Z equals that list. All right? It's going to create a variable, and what it stores in there is not the list. It stores where you can find the list. We call this a reference. Okay? Do you remember how I was saying, like last time or maybe the time before, where I'm like, well, you know, technically when I say A equals some list or whatever, A is not storing a list, it's storing a reference to a list, but often we just say, oh, it stores a list, but really it's a reference. Yeah, this is how it works. This is what I mean by that. So now, when I say Z, the computer knows, oh, okay, well, I got to go here. Okay? Now, also, by the way, think of the offsets, right? Remember how we indexed based on 0? It means, okay, go to the beginning and take 0 steps, right? So when you index, you are like going into here to access individual things. Cool, right? So that's how this is designed. Any questions yet? Really? So everyone's happy? Yes?
Isn't this similar to like how data recovery works? Because when you delete data on your computer, it just gets rid of the thing that leads leads to the actual data.
Yeah, so so data recovery kind of. So usually what happens with that is you would like implicitly do that, and when in reality with like when you delete something, you just go like, okay, this is just marked as like unused, so it can be overwritten. There could be references that still exist, but you just don't care about them anymore. But we will learn about something called garbage collection, which is going to be more aligned with what you're saying, I think. But you've got the right idea. You absolutely do have the right idea. Other questions? All right. Now, what do I have this? Okay, take a moment looking at this. Why do we start counting at 0? Well, I just spoiled that one for you. It means go to address 677 and take 0 steps. Okay, great. Take 1 step, 2 steps, and so on. All right? Now, if we want to make a copy of Z, now this is where we're getting into this, right? This would have been like if I said Z. All right? If I want to make a copy of Z, we do it the same way we did it with the primitive types. The exact same way. But be careful with what I said. If I want to make a copy of Z, what's Z? A reference to a list. It's not a list. So if I want to make a copy of Z, I would write something like W equals Z, like this. But what gets copied? It's the same as it was with the primitive types. With 17, I went to that memory address, copied the contents of that memory address, and put it somewhere else. Here, I go here, I copy the contents of this memory address, it's a reference, and put it somewhere else. But what do I effectively have? I have 2 references to the exact same one list. There's only one list. You see what I mean? Do you see? And you're like, what do you mean there's only one? Look, I mean, literally there's only one A, B, C, D, E, F, G, H here. There's only one. But I have 2 references to that list. And that's what happened here. Let's draw it. L is a variable that contains A, B, C, D, E, whatever, good enough. Right? Then I say my other list equals my list, OL. I copy the contents, which is another arrow. All right? So then when I say my other list at index 0, so I go my other list, oh, index, that's here, become X. Both references are referencing the exact same one list. So no matter if I go through here or through here, I get the modified one list. You see? This is super important to understand. I'm going to tell you right now, you are going to mess this up for the rest of your life. Not because you're new programmers, but because all programmers are going to go like, ah, shit, it was a reference. Right, yeah. This is going to be something that screws you up all the time. You can be the most experienced programmer in the world. This is going to bite you every once in a while. It's going to happen. So pay attention to how this works so you could recognize when it happens. Assignment 3 is all about making you go insane dealing with this. So hopefully, once you get assignment 3 working and it makes sense, you got the hang of it. That's good. But we're on assignment 2 right now, so no worries. Any questions about that? All right. But the point here is, there's one list. I could have a billion different references to one single list, but at the end of the day, it's still one list. It's like saying, who wants to be a volunteer? You. Perfect. I've got this hand. It's pointing at you. And I'm going to say, through this hand, I'm going to tell you to raise your hand. Great. And now this hand goes like, what the hell? Why is his hand up? Well, because this guy told him to change it. Where this one doesn't know, but he can observe and be like, wait, you changed. What's going on there? This could be a nightmare. Now, by the way, this becomes, one sec, this becomes less of an issue. Remember how with strings we learned about mutability. You can put your hand down, by the way, yeah. Remember with strings we learned about mutability. Strings are immutable. You can't change them. Okay, once they're created, they're set. Lists, on the other hand, are mutable. You can modify their contents. Okay? This problem almost disappears if you treat everything as immutable. Because, so what if I have another alias? If I can't change it, I can't mess with it. It's fine, right? So this is one of the reasons why we love to make things immutable. Because it eliminates this nightmare of a problem that you will always have. So that's one of the reasons why we like things to be like stateless. Like you can't modify their state. You can't mutate them. All right? But as it is, lists are very mutable. So yeah. Also, you'll notice in assignment 2, if you're paying attention, I go out of my way to treat lists as if they are immutable. I always tell you, like, don't modify the lists. I say, like, have the function take the list, make a copy of the list, and modify that copy, and leave the original one alone, right? So you kind of pretend it's immutable, and that's a good thing. Because otherwise, good luck. Questions, questions, questions. You had a question.
Oh, no, I was just stretching.
Okay. All right. So, and this is just saying, if I were to say, okay, Z at 0, 1, 2, 3, 4, if I changed it, both references, it's the same list. All right. This particular situation, like Z and W, the word we would use here is they're aliases. They're multiple variable names that get you the same one thing. They're aliases. Now, by the way, like the way Python, there's a lot more to how Python's going to work. Python's sophisticated, right? Really what would happen is you wouldn't actually have a list of your contents. You would have a list of additional references to other chunks of RAM that store what you're holding. So you get a bit of a nightmare of something like this. But Python hides this part and pretends that, like, oh no, as whatever is in here is actually there, even though it's references. Because that's how it would work traditionally, and Python's trying to make itself work how it traditionally worked for consistency. But it's pretty cool stuff. Questions, questions? Usually this topic is filled with questions. I'm shocked. Is it because you're all so smart? It must be, right? Yes, yeah, okay, all right. Awesome, makes perfect sense. The big takeaway here is if you're saying like, oh, so the computer makes a copy differently. No, it's always doing the same thing. It always goes and copies the contents of RAM. Copies this, puts it there. Copies this, puts it there. What's different, it's not even what's different. It's what's important to remember is what is stored in RAM. If it's a primitive type, that's your integers, your floats, your booleans. If it's a primitive type, it's the value. Even though in Python it's not, but it acts like it is. If it's literally anything else, it's going to be this. All right? Cool. To go back to that mutable example, why we like when things are immutable. Think of strings, right? Strings work like that. They're references. A equals hello, B equals A. But the fact that strings are immutable means I can't get to a situation where, oh, B at 0 equals X or Z or something, right? Like, I can't do that. I can't even make that change, meaning I can't get this like dirt muddying of the water. Like, it's impossible to make that mistake now. That's wonderful, right? Yeah, you get it. Yeah, cool. So the value of mutability, immutability, you know, being aware of that. Yeah, so be aware of what's stored in RAM. And if you're like, how am I going to remember? For us, integers, floats, booleans, they're just stored in RAM. Everything else is a reference. Okay? And you're like, well, what other objects are there? There's a lot. A lot that we will learn about, and it's easy, and very soon we're going to learn about how to define our own objects. So everything else is going to be objects. And this, for example, right? Remember when I showed you, where was it? This, right? This is like the reference. What was stored? Well, what's stored here? Well, it's a reference to where you can find the, where you can find the function. Notice how every time I hit run, it's in a different spot. It's kind of fun, right? Because the computer has to go like, put it there, right? See? It's always around 7FF though. 7FF of 2B. Yeah, there's a lot of RAM. Questions, 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 questions? No? All right. I really am concerned because usually there's a lot of questions right now. All right, okay, good, wonderful. I guess so. This is great. Yeah, I'm very happy. I hope this continues. Yeah. Cool. The only way you're going to make this stick is when you get your hands dirty, of course, like with everything, right? And that's kind of what assignment 3 is all about. Assignment 3 is designed to make you angry. So, yeah. And yes, it was intentional, but it's for your own good. So there you go. Assignment 3 is a really good debugging loop because it's visual. You're making like tic-tac-toe. And so like when you hit run, you can immediately see like, oh, what went wrong, right? And then you make a change, you hit run, and you can see how like the change you made affects what you see. So there's a really nice like debugging loop there. And so assignment 3, the big learning objectives for assignment 3 are like more familiar with lists. Assignment 2 is about lists and whatnot too. Assignment 3 is about lists, being aware of references, and also that debugging loop. Assignment 3 drills that debugging for you, so get ready to get mad. But remember, that's really programming. Okay. All right, aliases and some list trivia. Remember how I showed you like the string trivia, how like, oh, you can concatenate strings, you can do this, you can do that. I'm going to show you a couple of things you can do with lists. Now, here I showed you the example of, if I go here, right, this is just the example of what I just showed you. How, oh, if you modify the one list, the 0, 1, 2, and then you modify it through B, both are changed. Even though really it's not both are changed, it's the one thing that both things reference are changed. So, and also like, you can think of this from, okay, I showed you why, right? Like I showed you, well, how? Well, okay, this is how the computer stores it and whatnot. But think of it from like a practicality standpoint too. Imagine if I had a list of size like 1 billion. And I said, okay, A equals list of 1 billion. Do you think your computer is going to be happy making a copy of 1 billion things? No, it's not going to be happy, right? So references, great. They work great. Now, sometimes you do want to make a copy. So when you do want to make a copy, you got to know how. But yeah. All right. So remember A and B, they're both references. Yeah, the idea of references goes well beyond lists. Don't worry. When you do want to make a copy, there's 2 easy ways to do it. SUMList. So imagine you have a list called SUMList. You want to make a copy of it? Use the method .copy. Boom. It returns a new list that's a copy of the first one. Great. Another one too is, here's like a shorthand way of doing it. Who remembers what this is called again? Slice. Nailed it. So this means take a slice of it starting at, when you don't put a number before, what does it mean? Start at the first thing, the beginning, 0th thing, whatever. When there's nothing at the end, go to the end. And if you don't have a second one, it means count by ones by default, right? So this means go and give me the list of everything from the beginning to the end, right? So this will make a copy of that list, by the way. So that's another easy way to do it. If you're asking me, I would argue that this one's a little better to use because it's a little bit more self-descriptive code. If I'm a Java programmer where slicing like that doesn't exist and I see like some list.copy, I'm going to go, that probably copies the list, right? But if I see this, I'm going to go like, what the hell is that? That makes no sense, right? So there's something there. Although I probably do this every single time, even though I would prefer that. To each their own. All right, cool. And we might as well stop here because there's no time for anything else. All right? Cool. Last chance for questions? Okie dokie.